All right, so last we're going to cover unit steps and impulses. You covered this first in circuits 2. So let me just remind you about what unit steps are and a couple of their properties. The first, this is what they're called. If you were to draw it, it looks like that. What does it do at time equals 0? I said mathematicians worry about that. We don't, since there's no energy in that signal at exactly a moment in time. So what it does is irrelevant. And then last, we can define it by saying it's 0 for time less than 0 or 1 for time greater than 0. And I'll just arbitrarily say or equal to, although it doesn't make a difference. Now, the last rule I want to talk about it is what is its Laplace transform? What is the Laplace transform of U of t?
1 over s.
1 over s, yeah. All right. So now let's do the same thing for our impulse. Now our impulse, its picture is an arrow pointing up to infinity with 1 in parentheses. That doesn't mean it goes up to 1. It goes up to infinity, but it has an area of 1. And just, although this is what its graph looks like, what I want you to think about intuitively is it's the limit as delta x approaches 0 of a tall, thin rectangle that's getting squeezed down, and that has a width of delta x. So it's being squeezed to nothing, and it has a height of 1 over delta x. So if delta x is really small, its height is really big. Think about a balloon, and as you're squeezing it, it's getting taller and taller and taller. Its area is always width times height. Its area stays 1, but it's squeezing down infinitesimally thin until finally you get something that's 0 everywhere except at 0 where it's infinitely high, but when you integrate it, you get 1. So this is how I suggest thinking about it in your intuition. But the left is how it's actually drawn.
So, sir, that symbol you wrote, is that what is that called?
That's called the unit sample. So this is the unit step function, and this is the unit sample.
And that's
function.
like an S. That's like an S, but that comes back around.
Oh, it's the Greek letter del, and it's like a 8 that's missing part of it. Linguistically, it's related to a D. And that D is related to this delta X here. So it's infinitesimally narrow and infinitely tall. So this is, sometimes you'll also hear called del, or its whole Greek name is delta. It's a lowercase delta. Lowercase in Greek is delta, and the capital is capital delta, which is how they're related.
Sir, I have a quick question.
Mm-hmm.
So on the formula sheet, or first of all, the impulse is the integral of the step function, right? Or the step function is the derivative of the...
Haven't gotten there yet, but yes, we will be talking about that in another moment.
So my question is that the Laplace transform of a unit step function is 1 over s, u of t, but the Laplace transform of del prime is just s. But aren't del prime and the unit step function the same thing?
No.
Okay.
No. Del prime is del prime. Del prime is a whole new function.
I thought del prime was like the unit step function. Like the derivative of.
You've got it the opposite way around.
Okay.
You got it opposite way around. It's not S, it's 1 over S. The prime, the derivative of the step is the delta. Let me talk about that at the end, because this is getting a little bit more advanced than where I want to go to. Let me finish up with this, and then I'll hit another way of approaching your question. There is no way to define del of t by saying it by in a linear piecewise fashion. You can't say it's 0 for t not equal to 0, and then it would be, I guess you'd say it's infinite for t equals 0, and then how do you somehow still get across that it has an area of 0? Just don't do it. Instead, realize that the transform of a unit sample is 1. Now, let me hit what Joe was alluding to earlier. You know that integrating things in the time domain, is like multiplying by 1 over s. And taking a derivative in the time domain is like multiplying by s. So integrating is like dividing by s, taking the derivative is like multiplying by s. How are unit step and unit sample related? They're also related by calculus. So a unit step is what you get. What can you do to this unit sample to make it into a unit step? If you integrate it from left to right, you can see it's going to be the integral, the area underneath this unit sample is 0, 0, 0, 0. And then at 0, all of a sudden it becomes 1, 1, 1, 1, 1. So the unit step is just the integral of the unit sample. And that means that the unit sample has got to be just the derivative of the unit step. And to see that physically, what's the slope here? It's 0, 0, 0, 0. And then all of a sudden, at this moment, it spikes up to infinity. And then once again over here, the slope is 0, 0, 0, 0. And that describes the unit sample exactly. So now what Joe is alluding to is that if this is true, if this part is true, we should be able to take the derivative of this, which is 1. I'm sorry. If this is true, we should be able to take the integral of the unit sample, which is this. And taking the integral is like multiplying by 1 over s. And sure enough, in the frequency domain, we get 1 over s times 1, which is 1 over s. On the other hand, if the unit sample is really the derivative of the step, and the derivative is really like multiplying by s, we should be able to multiply the unit step by s to get the unit sample. And sure enough, when you multiply the unit step by s, you get s over s, which is 1. So that's the integral differential relationships between u of t, between the unit step and the unit sample. And what Joe is saying is that we could even go further. If we want to, so these are properties. Now we're going to talk about some pairs. And although this goes a little bit further than I was intending to in this lecture, if u of t transforms to 1 over s, and if we go to take the derivative of u of t, to get our impulse, that's just like the derivative is just like multiplying by s, so that gives us 1. You could conceivably go on one more step and take the derivative of your impulse, and you'd get something we haven't talked about yet, and I wasn't planning to, called a doublet, and then that has a transform of s. And similarly, you could go in the opposite direction. You could take the integral, and when you take the integral, it's multiplying. It's the integral is like dividing by s. The integral is like dividing by s, so that's s over s is 1. You can take the integral, and they get 1 over s. You could take the integral one more time, and what's the integral of u of t? Can you kind of see it? If you take the integral of something that looks like this, what do you get?
Is it just t?
Yeah. Well, it starts off at 0, right? And then it just becomes t over here. This would be u of t. Because as you move over, your area gets bigger and bigger. And so therefore, we're going to call this thing t times u of t. And therefore, this would have to have a transform of 1 over s squared. And you're just marching up the line. And if we go back to our transform pairs, you'll see that this transform pair actually does exist. And you can keep playing that game on ad infinitum. You could do another integral, and you'd end up having something that's now 1/2 t squared. And then that would have a transform pair of 1 over s cubed, and so on. If you guys don't get all that, I don't care. That's a more advanced application. But what I do care about is that you know what the transform is of u of t, what the transform is of the impulse, and what they look like intuitively.